Hello. So before we get started today, I want to kind of recap on what we've done so far in this class and then where we are going to go in this lecture. So far in this trigonometry class, we defined our trigonometric functions, looking at right triangles and the ratio of sides of an angle. And then we had looked and extended that to the unit circle, using the unit circle to help us find angles of a trigonometric function using reference angles or coterminal angles, using the fact that our trigonometric functions are periodic. We're now going to jump in and graph our trigonometric functions on the XY plane. And before we do that, I wanted to kind of review a little bit of college algebra for you that would help us when we go in and start graphing these functions. So this is just a very quick review. And so in this lecture, we want to review the properties of functions and their graphs. We're going to look at the domain and the range, define what a function is. We're going to look at vertical asymptotes, symmetry. So we had talked about our trigonometric functions being even and odd. So looking at that fact to help us graph these functions. And then we're going to look at the translations of graphs. So vertical transformations, horizontal transformations, reflections, and stretching and shrinking. So that is just going to be a quick kind of review of those things. And then we're going to jump in and start graphing our trigonometric functions. So let's look at and recall what the domain and the range is. So when we have a function where our domain are all the values that we can plug in to the equation function that would give us back a real number. The range are all those outputs that we're getting when we plug in a value that's in our domain. And so the definition is in front of us. The domain and the range are two main factors of functions. The domain of a function is the set of input values of a function, and the range is the set of all function output values. A function is a relation that takes the domain values as input and gives the range as output. So the primary condition of a function is for every input, there's exactly one output. So in order to be a function, if we put a value in, we're going to get back one output. If we get back multiple outputs for that one input, then it's not a function. And you might recall that you could use the vertical line test to see if something was a function or not. So if we were looking at a parabola, for instance, this is a function because every input we put in here, every x value just gives us back one y value. So this would be a function or an example of a function, where if we looked at a circle, that would not be a function. So here, our circle, here's an example where one of our inputs, which is defined for this circle, gives us back two separate y values. And so that is considered not a function. Okay, so looking at our trigonometric functions, we'll see that they are indeed functions. We have been looking at putting in the angles into the trigonometric functions. When we extend to this to the XY plane, we're going to look at the values that we plug in being real numbers. Okay, so here is an example in front of us. And it says f of x equals x squared plus 2 plus 4. And so just the following wants to know is 1/3 on the graph of f. So if we're given a point, we know that point is satisfying and is on the graph of that function. If you plug in those values, in this case, x is equal to 1 and y is equal to 3/5, or f of 1 is equal to 3/5, another way to write that. meaning the same thing. If we plug those values in for x and y, we're going to get back a true statement. If we don't get back a true statement, then that's not a point on our graph. And so in this case, in this example, if we plugged in 1 wherever we see an x, is that equal to 3/5? So let's plug that in here. So is 3/5, is this equal to, wherever we see an x, I'm going to put a parentheses, and then we'll go back in and plug in 1 wherever we see that parentheses. So we have x squared, so parentheses squared, plus 2, all over x, so parentheses, plus 4. In this case, we're plugging in 1 wherever we saw an x. So in this case is 3/5. Let's simplify this down. Is this equal to, well, 1 squared is 1, plus 2 all over 1 plus 4, which is 5. And so I can see my numerator, 1 plus 2 is 3. And so 3/5 is equal to 3/5. And so we can say yes. This 1 3/5 is a point on the graph. So if x equals 0, what is f of x and what is the point on the graph of f? So if x is equal to 0, we want to plug in 0 wherever we see an x in our function. So again, let's go through and plug in a parentheses wherever we see an x and plug in that value wherever we had a parentheses. So we have 0 squared plus 2 all over 0 plus 2. So simplifying this, we get that we have 0 squared is 0, plus 2 is 2, all over 0 plus 2, which is 2. And this is equal to 1. So if x is equal to 0, then we know that a point on this graph is 0, 1. So if f of x is equal to 1/2, what is x and what is the point on the graph? So sometimes we're given the y value of our function, and we're trying to figure out what is that input, in this case, the x value, which would give us that y value. And so part of this is just being able to read what it's saying and understand. And so in this case, we're given that our y value is 1/2. So we have 1/2 here is equal to our x squared plus 2 all over x plus 4. Oops, and I can see I just made a mistake down here. So I plugged in the wrong equation. So this should have been down here, 0 plus 4. It's 4 here. And so that would have given us 4 down here. So 2/4 reduces to 1/2. So 0 1/2 is actually the point there. Okay, so but going back up to this example, where we're given the y value and trying to find the value for x. So I have an equation and I have a rational equation where we have functions, we have values in the denominator. And so we can we can solve this by getting rid of our denominators by multiplying by our least common denominator. So I have a factor of 2 here, which is not a factor over here, so I need that in my least common denominator. And I have this factor of x plus 4 here, and so I also need that in my least common denominator. So using the rule that because this is an equation, I can multiply the same thing on both sides of the equation, and it will give me an equivalent equation back. So I'm multiplying 2 all times x plus 4 on both sides of my equation. And once I do that, notice that factors cancel. And we no longer have any denominators left other than 1. So distributing 1 to x plus 4, we get back x plus 4. is equal to, well, x plus 4 is canceled, but we're left with 2 times the quantity x squared plus 2. So distributing our 2, we get 2x squared plus 4. So once I clear my fractions, I would look at what type of equation I have, and I could tell that this is quadratic. So in order to solve a quadratic equation, I want to set this equal to 0. So I want to get everything to one side of the equal sign. So let's subtract x on both sides and subtract 4 on both sides of our equation. Use one thing to one side, we can do the same thing to the other side to make it equivalent. So we have 2x squared minus x. 4 minus 4 is 0, so we don't have to write that. So solving this quadratic equation, I noticed that we can factor out an x. So let's first start by doing that. Pulling out an x from both of those terms, we're left with 2x minus 1. So the right-hand side is completely factored. So now we can look at setting each factor equal to 0. So we're looking at when is x equal to 0, well, when x is 0, and when is 2x minus 1 equal to 0. So solving for x here, we could add 1 to both sides. We get 2x equals 1, and then divide through by 2. So we get x is equal to 1/2. So there's 2 separate points, 2 values of x that would give us back a y value of 1/2. So we have a point when x is 0, y is 1/2, and which we had seen up in part B. And when x is 1/2, y is also 1/2. So it's okay. This is still saying it's a function. We just have 2 separate x values that are giving us the same y value. So it's okay, that's legitimate for the definition of a function. So when you're looking, the next question asks us to find the domain of f. When you're looking for the domain of a function, usually I look at, are there any trouble spots? Is there any value in here that I can plug in for x that would not give me a real number? And so there's a couple instances where we would not get back a real number. That's if we have a rational equation, which we do. If there's any value which sets our denominator equal to 0, we have to exclude that from the domain. We can't divide by 0, it's undefined. And so that value which sets the denominator equals 0 doesn't give us back a real number, so we have to exclude that. If we had a radical, then we would have to worry about values which give us a negative number under an even powered radical. We'd have to exclude those values. So looking at my function f of x equals x squared plus 2 all over x plus 4, there's only one value I need to exclude, and that's the value that sets the denominator equals 0, which is x equals negative 4. So we're looking at when is x plus 4 equal to 0, x equals negative 4, and so x cannot equal negative 4. So there's a couple different ways that we can write this. A lot of times in mathematics, you're going to be using interval notation. And so this interval notation for the domain, there are all the x values that we could use, which would all the x values that we can use. So all the x values in this case that are in the domain. And so if we look at this, x cannot be negative 4. We're looking at all the x values coming in from negative infinity all the way to negative 4. For interval notation, if we don't include that value on the interval, then we use a parentheses. If negative 4 was part of the solution, we would use a bracket there. But we're excluding negative 4. We can get really, really close to negative 4 on the left-hand side. So negative 4.1, negative 4.01, negative 4.00000001. So there's an infinite number of things getting very close to negative 4, but not getting there. Plus union, we're looking at all the values from negative 4, not including, so parentheses again, to infinity. So this would be our domain. Of that rational function. Part E, it wants us to find the x-intercepts of any, if any, of the graph of f. So recall x-intercepts, any value that we're crossing or touching the x-axis is considered the x-intercept. And so if you think about it, when you're on the x-axis, any point on this x-axis, your y value is always 0. So for x-intercepts, to find those, you're going to let y equal 0. Or another way to say that, f of x is just another way to write your y value, your output. Or let f of x equal 0, and then we're going to solve for x. So in this case, we're going to let f of x equals 0. This is equal to x squared plus 2 all over x plus 4. Again, I have a rational equation here that I'm solving for. And so I want to clear my fraction. I can clear that fraction by multiplying by my LCD, which is x plus 4. Well, x plus 4 times 0, that's just 0. This is equal to x squared plus 2. So a couple ways I can go about solving this quadratic equation, x squared plus 2. I could factor it. I could use the quadratic formula, or it's in the form where I can use the square root method. And so since I have a perfect square x squared here, and all the other terms don't have an x in here, if I subtract 2 on both sides, I get negative 2 equals x squared. Now I can take the square root of both sides. So when we take the square root of both sides, we're putting plus or minus. I just do it on the one side. And I usually do it with the number. And so plus or minus the square root of negative 2. That's not a real number. That's an imaginary number. We get x is equal to plus or minus I root 2. So since this is not a real number, this tells me that we have no x-intercepts. So list the x-intercepts of any of the graph of f. There's none. So list the y-intercept if there is one, and graph the function of f. So the y-intercept, if we go back and look at the xy plane, our y-intercept, any point that would fall on this y-axis, the value of x is always 0. So to find the y-intercept, we're going to set x equal to 0 and solve for y. So x equals 0 and solve for y or f of x. So going back up into our equation and plugging in 0 wherever we see an x, we get y is equal to 0 squared plus 2 all over 0 plus 4. which gives us 1/2. Two-fourths, which reduces to 1/2. So the y-intercept, there's only one, and it's crossing when y is 1/2, or at the point 0, 1/2. Okay, so there was just an example of kind of looking at points, how to find points of, or to tell if a point is a point on the graph of a function. Just getting familiar again with a notation, function notation, looking at the domain x and y intercepts. So we'll be extending these concepts to our trigonometric functions in a little bit. So I have another question in front of us. So this question is just to look at a graph of a function, be able to interpret it, what the question is asking us to do, and answer the questions. So we're given this picture of a graph of a function in front of us. And first question says, find f of 0 and f of 6. Well, what this is telling me is this f of 0, this is saying, what is my y value when x is 0? So I'd go to the graph and I would look at what is x equals 0, where is x equals 0, and that's at the origin. So I can tell here that at 0, x equals 0, my y value is 0. So f of 0 is equal to 0. F of 6, so same sort of idea. In this case, though, x is equal to 6, and we want to figure out what y is there. So when x equals 6, we get y is also 0. So f of 6 equals 0. F of 2, same idea. This time, though, we're looking at when x is 2. When x is 2, I go down here and I see that I have a point at 2, -2. So f of 2, my y value is -2. So f of 2 equals -2. And f of -2, so when x is -2, my y value in here is 1. Is f of 3 positive or negative? So it's asking me, when my x value is 3, is my y value a positive value or a negative value? So let's look at this. When x equals 3, between 2 and 4, if I look at what side my y value is, it falls below the x-axis. So f of 3 is going to be a negative value. Is f of -1 positive or negative? So again, I'm looking at this time when x is -1, is my graph falling above or below the x-axis? Above the x-axis, my y value is positive. And so f of -1 is a positive number. So what values of x is f of x equals 0? So it's asking me, what are my x-intercepts? What are the values where my graph is touching or crossing the x-axis? And if we look at that, there's 3 points where it's touching or crossing the x-axis. That's when x equals 0, when x equals 4, and when x is equal to 6. I'm going to erase some of the colors I have on my graph to answer the next question. The next question is asking, for what values of x is f of x less than 0? So it's asking for when is my function, when is my graph falling below the x-axis? And so I only see one piece of this graph that falls below the x-axis. And so when we state this, we're stating the x values of that range. And so the range, those x values fall below the x-axis. We can say this is 0 is less than x is less than 4. How we would write that, though, in interval notation is 0, 4. And both of the 0 and the 4 have parentheses around it because it's not part of the value. 0 and 4 is what it equals 0, and 0 is not strictly less than 0. The domain are all the values of x that we're using for the graph. If this graph had at the end values this arrow here, then it would be extending in that direction forever. But in this case, we have endpoints, and they're points and they're not open circles, so that tells me I'm including those endpoints. And so I notice because the graph is continuous everywhere between x equals -4 and x equals 6. And so my domain are all those x values. And so I can write it as -4 is less than or equal to x is less than or equal to 6. Or in interval notation, we're starting at -4, including it. So we have a bracket, -4, comma, 6, comma. Range are all the y values that our graph we're using. And so we need to look at all the y values. So look at this. My smallest y value in here is when x is -2. And my largest y value is when x is 3. So I'm hitting all the y values because it's continuous. There's no jumps in the graph. And so my y values, maybe it's a little off because of, are from y equals -2 and including. So -2 is less than or equal to y is less than or equal to 3. Or bracket -2, comma, 3, bracket. This is really the only time when we're using interval notation that we're using the y values. All the other times we're using x. So domain, we use x. If we're looking where it's increasing or decreasing, we use the x values. Range is the only time we use the y value. What are the x-intercepts? So looking at the graph, looking at where it crosses or touches the x-axis. We have x equals 0, x equals 4, and x equals 6. Y-intercepts, this is at the origin, so it's when y is equal to 0. How often does the line y equals -1 intersect the graph? So y equals a number. Recall that's just the horizontal line going through that number. So y equals -1. So I would locate where -1 was on the graph, which is right here. And then I would draw a horizontal line. So notice that there's 2 spots, 2 x values that give us a y value of -1. So it crosses the graph twice. How often does a line x equals 1 intersect the graph? So recall x equals a number. That is a vertical line. So x equals 1, I would determine where x equals 1 was. And then I would draw a vertical line through that. And so if I look at that here, it's only crossing once. For what values of x does f of x equals 3? So kind of what we had just done with the horizontal line, let's look at it at y. F of x equals 3 is when y is equal to 3. So I want to find all of the x values that give me y equals 3. So if I look at where y equals 3 is, and I drew a horizontal line, notice that there's only one spot in here. And that is x equals 5. So when x is 5, y is 3. For what values of x does f of x equals -2? We had just seen, oh no, that was -1. So find y equals -2. Again, if we did our horizontal line there, I see that it's only crossing the graph once. And the value of x, it gives me f of x equal 2, or y equal, sorry, -2, is x equals 2. So hopefully going through that example helped you recall some of those important terms and properties of graphs and how to find them and the notation being used. So next I want to talk about rational functions really quickly. Recall a lot of our trigonometric functions can be rewritten in terms of rational functions in terms of sine and cosine. And so a rational function is a function of the form r of x is equal to p of x over q of x, where p and q are polynomial functions. Well, we're going to be dealing with this with trigonometric functions, and q is not a zero polynomial. So we can't have values of q that set this equal to 0. It just can't be 0. The domain of R is a set of all real numbers, except those for which the denominator q is 0. So when we're dealing with our trigonometric functions, we have to worry about when our values of x or theta or whatever we're doing as our input is not setting our denominator equal to 0. If we have a value which sets our denominator equal 0, recall that we get a vertical asymptote at those values. So vertical asymptote. So let's just define that really quick. So there's a vertical asymptote. At, let's say, x equals a. Then as x approaches a, on the left and right, of x equals a, then f of x, or let's call it r of x, since that's what we had defined our rational function. Then r of x, our y value, goes to either positive or negative infinity. And it could be going both. It could be on one side, it could be going to positive infinity, and the other side, it could be going to negative infinity. So let's just look at a picture of what the graph would look like for a vertical asymptote. So let's say A was here. A lot of times we'll denote that vertical asymptote with a dotted line, even though it's not there. And as x is approaching A from the left, it's either going to be shooting upwards to positive infinity. So we could be coming up like this. On the right, also approaching positive infinity, or we might have it going up on the left, down on the right. Just different examples of what this might look like. They could both be shooting downwards or vice versa, with decreasing and then increasing. So this is what a vertical asymptote is. Vertical asymptotes, they occur at values which set the denominator equal 0, but not also the numerator. So vertical asymptotes occur when x sets the denominator equals 0, but not also the numerator. So if we looked at our trigonometric functions and we wanted to find our vertical asymptotes, well, sine of x and cosine of x, that is over 1. There's no value that sets 1 equal to 0. But our other trigonometric functions, so for instance, if we had f of x is equal to secant of x. Well, if we rewrote this, this is the same thing as 1 over cosine of x. And so secant of x is going to have vertical asymptote on values which set cosine of x equal to 0. So secant of x has vertical asymptotes. I'm going to call it VA for vertical asymptotes. Cosine of x is equal to 0. So if we looked at the unit circle, you can think about it. Remember, cosine of x was the x value on the unit circle. And so if we looked at the unit circle, the value when x is 0, or sets cosine of x equal to 0, that's going to be at pi halves. If we rotated this way, it would be 3 pi halves. Rotate again up to, so we could do more than a full rotation, or we can do a full rotation. So 5 pi halves, dot, dot, dot. 7 pi halves. Or we can say x equals pi halves. Notice this is every pi. So plus pi times k, where k is an integer. Okay, so we're going to have vertical asymptotes for our secant of x. If you look at the other trigonometric function that also has cosine x in the denominator, that would have been cotangent of x. So cotangent of x also has those vertical asymptotes there. So f of x equals cotangent of x, which can be rewritten as sine of x over cosine of, actually, I'm wrong. That's cosine of x over sine of x. So let's look at the other one, tangent of x. That's the one I wanted to see where cosine of x was in the denominator. So tangent of x, then we'll go to cotangent. So tangent of x, this is sine of x over cosine of x. So it also has vertical asymptotes at pi halves plus pi k, where k is an integer. Where if we looked at cotangent of x, and the other one is cosecant of x, that's where we're dividing by sine of x. Cosecant of x is the same thing as 1 over sine of x. So these are going to both have vertical asymptotes when sine of x is equal to 0. So looking at sine of x equal to 0, If we look at the unit circle, and we're looking at when is our y value equal to 0. And this was when x is equal to 0. X equals pi, 2 pi, 3 pi, 4 pi, ... So we can write that as x equals pi times k. Again, k is an integer. So those are where our vertical asymptotes occur for cotangent of x and cosine of x. And we'll talk about that more when we get into the graphs of those functions, but I wanted to bring in what we were talking about with vertical asymptotes into the trigonometric functions. Okay, so we looked at vertical asymptotes and how they're going to relate, and we'll see that again in the future when we start graphing our trigonometric functions. But we saw that our trigonometric functions, some of them will have vertical asymptotes. And again, those are the values which set our denominator equals 0, but not also our numerator. So looking at the following, we have, we're going to be using transformations sometimes to help us graph these trigonometric functions that has transformations with them. And so just to kind of review, so each graphing technique has a different effect on the graph of a function. Compressions and stretching change the proportions of a graph, and reflections change the orientation, but not the proportions. Vertical and horizontal shifts change the location of the graph without changing its proportions or orientation. So recall, when we're looking at a function, f of x, and we either add a constant or subtract some constant to that function f of x, so outside of that function, that's actually a vertical shift. We're going to say that our constant that we're adding is k, and k is always bigger than 0, so we don't have to think about adding a negative number or subtracting a negative number. So that k value is always positive. So if we add a positive number, this is going to take our graph of f up k units. So basically all you're doing is you're keeping your x value the same. But in this case, you're going to add k to your y value. That's going to give us our new point. So let's say you had f of x is equal to x squared. And we added 2 to it outside. And that would shift this graph up 2 units. If we looked at this and we subtracted a constant, or our constant was bigger than 0, this shifts our graph down k units. So in this case, a point that was on the graph before, x f of x, is going to become x f of x minus k. So if we subtracted 2, that would just shift that parabola down 2 units. If the constant that we're adding is actually inside the parentheses, so basically you're adding a number or subtracting a number to your value of x, and then plugging it in wherever you see an x in our function to get our y value. So they're saying if y is equal to f of x plus h, or h is bigger than 0, this shifts the graph to the left h units. So replace x with x plus h. So x plus h is going to shift it to the left. So it's going to keep the y value the same, but shift the graph to the left. So in this case, let's take our parabola x squared. So an example to the left would be f of x, let's say plus 2. So this is going to go to the left 2 units. So our vertex, where our y value was 0 before, is going to still be 0, but it's going to be negative 2, 0. Y is going to be 0. Where if we subtracted a constant h, that shifts it to the right h units. So if we had f of x minus 2, that would shift it over 2 units to the right. Then we have the example where you're plugging some constant, or you're multiplying some constant times your y value. So if we look at y equals a times f of x, where a is a number bigger than 0, we're multiplying the y coordinate of f of x by a. So it depends on if that number that we're multiplying f of x by, we know it's greater than 0, but is it bigger than 1? If it's bigger than 1, then it's going to stretch it vertically. If it's between 0 and 1, it's going to stretch it, compress it vertically. So basically, if our number is bigger than 1, that we're multiplying our y value, our graph is going to grow at a faster rate. So it's going to stretch it up faster. It's going to get skinnier. So this is a times f of x, where a is bigger than 1. Where if a was between 0 and 1, then it's going to, say, compress it. It's going to make it wider. So replace x by a times x in our point. So our point now is a times x, comma, y. Sorry. I'm reading the one below us. I'm like, that's not right. What we're doing here for our point is we're keeping x the same, but we're multiplying our y value by that number, a. So now looking at it, when we're multiplying the inside, the x value by a. So if y is equal to f of ax, where a is greater than 0, multiply each x coordinate, f of x, by 1 over a. And then we're going to stretch the graph if a is horizontally, if a is between 0 and 1, and we're going to compress it horizontally if a is greater than 1. Okay, so stretching it horizontally, it's growing at a slower rate. Let's say this is again x squared. So this is if a is between 0 and 1. if A is bigger than 1, let me just think about this for a sec. And if A is bigger than 1, then it's going to compress it horizontally. And so it's going to make it skinnier. So we'll be doing these types of operations to our trigonometric functions. And really what's going to happen is when we're looking at these values where we're looking at the argument not just being x, so maybe we're looking at cosine of 2x or cosine of 4x or cosine of 1/2 x. This is going to be changing the period of our functions. But we'll talk about that more when we get into the graphing of the trigonometric functions. Then we're looking at reflections about the x-axis and the y-axis. If you multiply a negative number outside, so y equals negative f of x, so that's changing my y value. So I think to myself, okay, if I change my y values, what's happening? Well, if I change my y values, that's going to be a reflection across the x-axis. If we multiply inside f of negative x, this is going to be reflected across the y-axis. Well, my one case with my parabola is okay with negative f of x. That would be a reflection across the f of x and reflected across the y-axis. So negative f of x will look like this. Problem is f of negative x, if I have my parabola like I do, it's just going to reflect, it's going to be a mirror image of the other half of the graph, so it's going to give us the same thing. So let's say you had this. And so if we looked at f of negative x, this reflects it across the y-axis. Change the color. And so we would get this as our graph, reflecting across the y-axis. So the last thing that may help us with graphing these trigonometric functions is recalling what it meant to be an even or an odd function. And we kind of reviewed this in the last week when we were looking at properties of trigonometric functions. So this should be a quick kind of review. But graphs of even and odd functions. A function is even if and only if its graph is symmetric with respect to the y-axis. And a function is said to be odd if it is symmetric with respect to the origin. Another definition is it's an even function if we plug in the negative value of our input. It would give us the same y value if we plugged in the positive of that value or the opposite sign of that input. So f of negative x is equal to f of x, then it's an even function. It's an odd function. If we plug in the negative of the x value, we get back the negative of what y would have been. So negative f of x. We saw that cosine of x is equal to cosine of negative x. So if we looked at it, which is a little kind of confusing because now when you're looking at this theorem, it's not technically kind of right. Like let's say that this was our x value here. And actually that x value in our case, when we're looking at this, we're looking at the that point and then determining our trigonometric functions. And that's going to give us the same x value as if we had done f of negative x. So negative x, we're going in the rotating clockwise. Where if we looked at cosine, sorry, not cosine, sine of negative x. So sine, that's our y value. So notice our y value here. That is different, going negative x this direction, is different than our y value up here. So that is giving us a negative, it's changing the sign. This is the same thing as negative sine of x. So cosine of x, this was even. Sine of x is odd. So any trigonometric function that has sine of x in it is actually an odd function. Any trigonometric function that just has cosine of x in it is an even function. So the ones that are even are cosine of x, secant of x. The ones that are odd are cosecant. Cotangent and tangent. So this can help us when we start graphing our trigonometric functions. We can use the fact that they're even and odd. Basically, this is telling me if I have a certain amount of points or know a portion of what the graph is going to look like, I can, knowing it even, I can reflect that across the y-axis to get the other half of the graph. If it's odd, which are 4 of them, we can reflect it across the origin to get the rest of the graph. So that is just kind of a reminder of some of those properties of functions, and hopefully that will help you when we start talking about graphing sine of x and cosine of x and the other trigonometric functions.